Hi guys, so today we're going to be talking about Lavoisier law of conservation. So as you recall from last class and what we did with fast chemical equations, we're going to be trying to prove it this time around. So first things first, let's recall what Lavoisier's law of conservation of mass is. Well, conservation of mass. We conserve mass. That mass is not gained or lost in a chemical reaction. That is fundamentally what Lavoisier's conservation of mass is. Reaction. Arc-Sanding reaction. Okay? So to prove so, we're going to do a science demo involving two chemicals. Chemical number one is called sodium bicarbonate. And then our second chemical is acetic acid. So we are playing around with acid here, so it's important for us to be kind of careful and wear the proper procedures. So, and I will have lab bottles here. That was dropped on the floor. And I'll wear this. So right now, I want first, Rochelle, can you please come on up and help me measure something? So right here, right now, I have 5 grams of measured sodium bicarbonate. And just to prove it, I want you to pour this into that small beaker. And you'll see the scale will move down. Awesome, right? So I'm going to move this exactly 5 places over, and we'll see whether or not this will balance properly or not. Is it around 0 mark? Gotta wait for it to stop. And if it is, then that's our 5 grams.
Not yet.
Not yet. All right, that's more or less a little bit okay, right? So let's say it's approximately 5 grams. So we have 5 grams of sodium bicarbonate. And the other thing we have here is 100 milliliters of acetic acid. We're not going to measure that because I already measured it for you guys just to save some time. Because we will be a little bit rushed. Okay? So in this reaction, we take 2 of these chemicals and we combine it together. And I'll write it down as the chemical formula. As Na being sodium and carbonate, CH3, AQ, or solid, sorry, because it is in solid state of matter, plus acetic acid, which is this. And what it forms is some sodium carbon and carbonic acid instead. And just for a review from last class, we're going to balance this chemical equation out. Okay? So as we remember, we write down the reactants on this side and the products over here, and then we list all of our chemicals. We have sodium, carbon, hydrogen, and oxygen. And let's just count whether or not on each side, whether or not it is balanced. You see 1 sodium over here and 1 sodium over here. That's balanced. Now let's do our carbons. 1, 2. There's 2 carbon over here and 1, 2. Oh, there should be 2 carbons. See, 2. 2 carbons, 3 carbons on each side. And for hydrogen, we have 1, 3, 5. 5 on this side, and 3 and 5 on this side as well. And lastly, the oxygen. We have 3 here, 2 here, 2 here, and 3 here. So I guess you have 5 and 5 over here. And by judging this, the number of reactants atoms and the number of product atoms are now all equal. Now the sodium, carbon, and hydrogen and oxygen are all equal. And so the chemical equation is balanced. There's no need to add any additional numbers on here as this seems to be the same. Alright? So we verified the chemical equation is balanced, there's nothing to change. And we also made sure that we have the same amount of what I said, 5 grams. And we also have 100 milliliters of this carbide, classed with acetic acid. So I'm going to record down some numbers for you guys just to make sure that we are all on the same page. On your worksheet, I believe Rochelle has, write down the objects that we have. We have an Erlenmeyer. We have 3.5 grams. A quart is 0.1.5 grams. Acetic acid, which I measured 100 milliliters, but it's 91.6 grams, and baking soda has 5 grams. Sodium bicarbonate. As 200 and as 5 grams with a total of 201.7 grams. Okay. So with this, let's see right now when we mix it, what will happen, and you guys are gonna predict what is the mass of our product, and explain kind of why would it be what it is. So, I'll give you guys a couple of minutes. What do you guys think when I mixed in the baking soda into this Erlenmeyer, and what's the total mass? What do you guys think?
I think it'll be the same.
So you think it's to be 201.7 grams, correct? So let's double check this. Let's take this right here, and I'll put it right here in here, and we'll see what happens. And also, when you guys are doing this, please observe and write down anything you guys see as the result of a chemical reaction. So what's happening here? So if I said 201, I'm going to flip this over to 201. All right, let's have that reaction kind of fill out. All right, so can someone tell me right now, what do they see in chemical reaction? What's happening?
It bubbles.
It bubbles. What does it mean by the bubbles? So there's forming of what? Forming of gas, correct. So as you're forming the gas should stay in here, correct? In the mass, right? So did you think that your mass should be exactly what we initially started off with? If gas stayed in there, that's right. So what does that say with our kind of results for this current part one of the demo? Well, it says that maybe the things that we experiment, you always not always have to include that everything that is made is still in there. As we all breathe out, we see that, oh, it's making some kind of gas. Does anyone know what kind of gas it is?
Carbon dioxide?
Carbon dioxide, maybe. How do you know? Doesn't say so in the chemical formula, does it? Not really. Well, let me explain. So here, when we form this compound here as carboxylic acid, it actually goes into a chemical reaction right by itself. That it's spontaneous for it to be unfavored in this form and go straight making into something else. And as you suggested, that you said it made carbon dioxide. What else do you think it made? Judging on this chemical formula, what do you think it has? What atom am I missing? Water. Why water? Because it has what? Well, think of it as it has a hydrogen here, right? If the chemical of Lavoisier's law of conservation says true, then the particles, the atoms of hydrogen cannot be destroyed. So it cannot be making just solely carbon dioxide. It has to make something with hydrogen. And the most common thing you can make see is water, H2O. And let's count out with the chemical equation, see where not the blank atoms are all balanced again. So reactants, products. What are our three elements? We have carbon, oxygen, and then hydrogen. We have one carbon here, three oxygen, and two hydrogen. This is the same thing on the other side. 1, 3, and 2. Is that a surprise? No. Because Lavoisier's conservation law says that they have to be the same. All right, so let's do this experiment one more time, and we're going to assume, and it is, I did an experiment. This is 5 grams of sodium bicarbonate, and we also have here the veil, and a balloon attached into it, at the end of it. Oops. I'm not correct. This was on really tight. Okay, so I take my sodium bicarbonate, and I'm going to pour it in here, and you guys think that seems to have right? A gas will form, and then what do you think happens to the balloon? Wait, cool. Oh, well, that happened. That's okay. So what's happening here? It's making gas, I'm trapping the gas, so it's building up. Pressure, right. So Ben, can you turn it off and flip up the match for me, please? Sure. So Ben right here is going to light a match to create a flame. And you propose that this gas is what? CO2.
Oh, no.
But are you sure it's CO2? Well, we got to make sure. How do you know there's no oxygen here instead? Yes, I do. Okay, I've lost it. So if this is carbon dioxide, it should extinguish the flame now, should it? right? Because flame need oxygen. Oh, it's slowly dying, and let's just make it last one more time. There you go. So the flame goes out because that is deprived of oxygen because all of the gases being formed are carbon dioxide. So what does that say? Well, it's relevant, and let's flip on to the next page. It's relevant to us because what happens is we are actually using carbon dioxide to extinguish fires sometimes. When there are fire extinguishers that are made of purely carbon dioxide. So we can use carbon dioxide as a fuel to extinguish fires. So that's the kind of a practice that we undergo in our daily lives, or firefighters sometimes use, because carbon dioxide is a harmless gas that we can breathe in and breathe out. Now, one of the questions I want to ask you is that, how can we prove that this gas that we made was actually carbon dioxide? Like I said, even though I used it to extinguish the flame, it might have been any other gas that was not flammable or replaces oxygen. So we know that since the flame went out, it's definitely not oxygen. But how can you guarantee that it's actually carbon dioxide? And in addition to that question, I want you guys to think that would the testers that you propose be able to distinguish between carbon dioxide and carbon monoxide? And that's a really important thing because breathing in carbon dioxide is fine until you suffocate eventually, but breathing in carbon monoxide will be very deadly as it binds permanently to your lungs and stops you from breathing. So at the very end, because my experiment kind of messed up, I wasn't able to measure out the mass of my gases properly, so build up my pressure. I believe that is the end. So thank you so much.